All right, well, good morning. Welcome to another fun-filled day of calculus. Today's plan, obviously, after going over homeworks and whatnot, we're going to go ahead and move into the next section, which is some more geometric applications of the integral. Specifically, we're going to look at...
Bruce shaved. Now he doesn't look like Duncan.
Yeah, right. Now I look like a normal human being. But
like
that's true. All I needed was the top hat, and I totally would have been Dr. Demento. I never thought about that. But the applications we're going to do today, we're going to look at arc lengths. We're going to see how we can use integrals to figure out the lengths of curves, and then look at surface areas of solids of revolution. So we've seen how to find volumes of them, and today we'll talk about surface areas. So, and then with whatever time's left, we're going to review a little bit for the exam that's going to be on Friday. So that's my plan. But as always, I want to start by letting you know that I'm open to looking at homework questions. So any that we'd like to look at, any questions that you want to address? All right, Antonio, number 7, I need to know what section. Okay, 2.3, thank you. And then I see Diego, you gave me 2.3, number 8. All right, so I'll put those on my list. All right, any others? All right, well, we'll start with those and we'll see how this goes. So let me go ahead and share my screen. All right, so 2.3, we have volumes of revolution using cylindrical shells. All right, so for number 7 here, it says we want to use cylindrical shells to find the volume of the solid obtained by rotating the region bounded by the graphs of y equal x, y equals 10 minus x, and the x-axis about the x-axis. Okay, so my suggestion first, as always, is draw the picture. Draw the picture of this region so you have an idea of what it looks like and how this is going to be shaped once we rotate about the x-axis, and then we can address the shells. So let me go to a whiteboard. All right, so here are our axes and the equations of the line. We had y equals x, y equals 10 minus x, and the x-axis as our third. Okay, so y equals x. Hopefully you guys all remember what that looks like. That's just the line that goes through the origin with slope 1. 10 minus x. Well, that's got a y-intercept of 10, and it's got a slope of minus 1, so it does something like that. And then the x-axis, of course, is this guy down here. So the region that we're rotating is this triangle right there. And we're going to rotate it about the x-axis. All right, so let's think about what that shape's going to look like if we rotate it. There's going to be a piece over here, and it's going to be circular. So it's going to kind of look like a top, sort of, a little spinny top. Basically, it's a cone on top of another cone, right? So think 2 ice cream cones stuck together with their with the round ends put together. That's what this shape is. All right, so that's our solid. So now let's set this thing up to do cylindrical shells. So if we're going to do cylindrical shells, let me draw in a representative cylinder. So there would be one of the cylinders that we get for that given height and everything. that's going to be our cylinder. All right, so we okay with the picture? You kind of see what's going on, I hope. So now let's start setting up our integral. So what we need, remember in general, it's always the integral of 2 pi r h. So anytime you're doing cylindrical shells, it's 2 pi r h. So just think of it as the 2 pi r, that's that circle of the cylinder. The h brings us down. So that's giving us the cylinder itself. And then the delta r, the dr, is giving us the thickness of the shell. Okay, so now let's start figuring out what these things are going to be. So in this cylinder right here, here's the r. Right? Here's the h. And then the dr is just a little tiny thickness. All right, so let's start getting this guy set up. We're going to have 2 pi. The dr is going to be a dy, because think about that thickness. The thickness of this is a little y chunk. All right, the radius is going to be given by the y coordinate, right? If this is our radius, that's our y coordinate. So we're going to get a y. And then our height has to be the difference in these two functions. However, I need these as functions of y, not functions of x. So we'll just rewrite these real quick. The first one's easy. That's just x equals y. The second one, if we solve that for x, it's x equals 10 minus y. And so that's what we're going to use to get our h. Our h is going to be 10 minus y minus y, right? When we're dealing sideways, it's always right minus left. So 10 minus y minus y. So that's going to be 10 minus 2y. So there's our 2 pi, our r, and our h, and our dr. So basically, if you tell me the y, if you tell me where I'm drawing this little vertical line, or sorry, horizontal line, I plug that in, that's going to give me my radius and my height of that cylinder. Okay, but now I want to add up all of those cylinders. I want to add up the cylinders for all of the y's that are in this region. So my lower bound is going to be 0 because that's where my region started. So think back to the original blue dashed region. Its lowest y was right here. So then the question is, what's the greatest y? What's the y coordinate of this point? Well, that's where we have to do the intersection business, right? We want to set these equal to each other. So we need y to equal 10 minus y, which gives us y equals 5. So we're going to agree from 0 to 5 for this one. So I hope this illustrates why I like to draw the picture, because it really helps me see all of this. It helps me see the bounds from 0 to 5, helps me show how the heights are formed for these. And I just drew in a random one of these cylinders. I just made sure that the x-axis went right down through the center of it. And I knew I needed that to go right down through the center of it because that's the axis about which I was rotating. All right, so I think I'm going to leave this one here. You guys know what to do. You're going to distribute 10y minus 2y squared. You're going to integrate that, put in your bounds 0 to 5, and from here it's what I like to call monkey math. Right? It's not thinking anymore, it's just do it. All the thinking was done to set it up. All right, so is this one better for 7? Questions on this guy? All right, well then let's go take a look at number 8. Okay, so same idea. We just have a different region now, right? So we're going to use cylindrical shells to find the volume of the solid generated by rotating the curve. Y equals 9 natural log of 7. Or sorry, natural log of x. Whoa, I don't know where that 7 came from. about the x-axis for x's between 1 and e. All right, so let's do the same thing. Let's draw the picture, see if we can get a representative cylinder in there, and then build our integral. So we'll go back to the whiteboard. Okay, so this time our function is y equals 9 natural log of x. Now this one you may not know as well, but you should be able to at least use your technology to graph it, but it's going to look something like that. It's an exponential that's been turned on its side. And we're going from x is equaling 1, which is that intersection point, out here somewhere, e. So the region that we're integrating, or that we're rotating, is this piece. And again, we're going to revolve it around the x-axis. All right, so before I do my revolutionary thing, hopefully we're all good with this picture and the region. So now when we spin that around, we're going to have that, right? And so we kind of get this thing. So this is definitely looking more like a bowl, a solid bowl. And let's think about what those representative cylinders will look like. So here's one of them. So again, since I'm rotating about the x-axis goes right down through the center of that cylinder. So there's one of my representative guys. All right, so let's start setting it up. Again, it's going to be the integral of 2 pi RH dr. So we're going to get 2 pi. We need the radius. Well, the radius is right here. The radius is going to be given by y. The height is right there. And notice that the height is always going to be related to our function value. We just have to subtract it off. But I need it as a function of y. So let's solve this thing for x. So we're going to get y over 9 equals natural log of x, or x equals e to the y over 9. So our height is going to be e minus e to the y over 9. And then our thickness is again going to be a dy, since we're going about the x-axis. Okay, so again, 2 pi, here's our radius, and then our height. So e minus the function value, which is e to the y over 9. All right, so lastly, we need bounds. We need the y values for this original blue shaded area. The lowest y is 0. So the question is, what's the highest y? Well, that's going to be when x is equal to e. So if I plug in e here, I get y is equal to 9 natural logs of e. The natural log of e is 1. So that gives me y equals 9. So the highest point on this is y equals 9. All right, so there's the function that we need to integrate. So at this point, just punch it into your calculator, or again, distribute and all that. But that's the setup here. So notice how similar these two problems are, at least in terms of the construction of everything. Obviously, we have different things that are defining like our heights and all that, but it's really the same idea. And usually when you're rotating about the X or Y axis, your radius is going to be either Y or X, depending upon which one, usually. It gets funky when our axis moves off of one of the coordinate axes. All right. So there you go. There's a little bit, a few of those from 2.3. All right. Anything else before we dive into the next application here? We good? All right. Well, then I'm going to hop up to the whiteboard and I will see you guys in just 1 second. All right, so we've now seen a couple of applications, right? We've seen areas between curves, right? So we've seen how we can use integrals to get areas, and we've now seen volumes, how we can use integrals to find volumes of solids. And for the solids of revolution, we really had two different methods, right? There was the disk/washer method, and then the cylindrical shells method that I just showed you. All right, so cool. But there's some more geometry stuff that we can do. And I'm going to show you two more today. And so the first one I want to talk about is arc length. And arc length is exactly what it sounds like. This is finding the length of a curve. So imagine that I gave you just some curve like this, and I said, find out how long that is. Now in the real world, this wouldn't be that difficult. You just lay a piece of string on top of it, and then straighten it out and lay it against a ruler, right? It'd be pretty easy to do. However, we don't have a piece of string. I don't have a piece of string handy. I definitely don't have a ruler handy. But let's see if we can figure out a way to get its length using calculus, using just math. Okay, well, to do this, we probably need to remember how to do arc lengths of easy ones, which are line segments. So suppose I gave you a line segment, the easiest curve out there, and I said, determine its length. How do you do that mathematically? Does anybody remember how you find the length of a line segment?
Distance formula?
Yeah, it's just the distance formula, right? It's the distance between these 2 points. So if I told you this point, right, this one, call it x1, y1, the other one, x2, y2, hopefully you remember that there is a distance formula, and it's the square root of x2 minus x1 squared plus y2 minus y1 squared. So it may have been a while since you've seen it, but hopefully that at least brings back some memory. You kind of go, oh yeah, I kind of remember seeing that. Does anybody remember where that comes from? Like, why does that equation give us this? It's mostly
something also to do with triangles and
so,
building pyramids. I would guess. I'm making a guess.
But I would say it's not awful. It's just the Pythagorean theorem, actually. If you were to draw in these guys here and make this a right triangle, we know the Pythagorean theorem holds. The good old a squared plus b squared equals c squared. And look at what those different lengths are. The one that we're curious about is d. if you look at this vertical one, that's the change in the y. So that's the y2 minus y1. This horizontal piece, that's the change in the x's. And if you just set up the Pythagorean theorem and then take a square root to get just the hypotenuse length, that's where that comes from. So it's just the Pythagorean theorem. It's good to know where things come from. All right, well, anyway, so there's our distance formula. And to help us out a little bit, because this is really cumbersome to write, let's think of this instead as the square root of delta x squared plus delta y squared. So delta x is just the change in the x, and delta y is the change in the y. All right, so that's how you deal with a line segment. Well, we obviously don't have a line segment here. So what? How are we going to use this to help us figure out this length? Well, this is where you want to think like a mathematician. And you actually kind of want to think like how we define the integral. Remember when we did the integral, we started with the area question. We were trying to solve the area under the curve. And instead of jumping straight to the area under the curve, what did we start with? What was our first attempt at approximating the area under the curve? Okay, good. Thank you, Alexi. We use rectangles because rectangles were shapes whose areas we knew. Okay, so let's think about this arc, and we want to find its arc length. Let's start by approximating it with arcs whose lengths we know. Well, the arcs, the curves whose lengths we know, are line segments. So here's what we could do. We could start by partitioning again, breaking this up into a bunch of different intervals. And in each of those intervals, draw line segments. Okay, so if you look at my graph now, I've got my blue curve, the original curve that I was trying to find the length of. But what I did was I put a bunch of line segments that approximate the curve. So if I were to calculate the lengths of these four, they're actually four. I know this one might look like it's one long one, but it's actually broken into two. But if I calculate the lengths of those four things and add them up, that's going to be a decent guess for the length of this curve. All right, well, what would I do to make it a better approximation?
Make more lines.
Make more line segments. Split this up into tinier chunks, and in each of those tinier chunks, have another line segment. So instead of having those, let's see, maybe we've got this one, this one, and this one, and this one, and this one, and this one. And I am just drawing line segments here. I'm not drawing curves, right? But if I were to do those, think about those green line segments. I don't know how many I have, on the order of 15 or so. They're going to fit that curve much better. Okay, well, what if I go to 100 line segments, or 1,000,000 line segments, or a Googleplex, real number, by the way. What about that many line segments? Well, clearly, the more line segments I have, the better the approximation. So this is when you start getting a little deja vu. Because this is exactly what we did when we found areas. We broke it into a bunch of pieces, made those pieces really, really small, and added them all up. Well, that means we're going to need an integral. All right. So here's how we're going to set this up. The arc length in essence, what we're doing, we're going to take a limit as n goes to infinity of the sum from 1 to n. So we're adding up a bunch of things, or making the number of those things get really, really big. But what I want is the arc lengths. All right, so this, of course, this limit of the infinite sum, or infinite limit of sum, is going to turn into an integral. But the form we have over here doesn't quite work out when we go to differentials, because if I go to differentials, I'm going to have both a dx and a dy. I can't integrate with both of them. I can only have one. So we're going to have to massage that a little bit. We're going to have to adjust it a little bit using algebra before we turn this into an integral. So I'm going to do that over here. Let me show you what I mean. So we're looking at this square root. So what I'm going to do is I'm actually going to factor out a delta xi squared. It's still inside the square root, but I'm going to factor it out of this bit. So the delta xi squared, that turns into a 1. The other piece, I have to divide out a delta xi. I don't have one, so nothing cancels, but I'm going to get this. Delta yi divided by delta xi, that whole thing is squared. Now, if you're looking at that algebra going, holy crap, what was that? It's just, I'm just dividing out a delta x squared. You can check it and see that if I distribute, I get what I started with. But this is a legit algebra. And now what I can do, I can pull out this delta xi squared. I can pull it out of the square root. The square root cancels with that square. So I get delta xi times the square root of 1 plus delta yi over delta xi squared. Okay, so let me just kind of circle this for a second because I want to highlight this. So this bottom line is equivalent, it's exactly the same as what's in there. Okay, I just did a little bit of algebra. But now let's look and see what happens when we take that infinite limit and that sum. So this is going to turn into an integral. Right? And it's going to be an integral from a to b, wherever our points are. But look at what happens to this. Okay, the delta xi becomes a dx. I'm actually going to put it at the end here because that's kind of what we normally do with integrals, right? And then I'm going to have a square root. In that square root, I've got a 1 plus. And think about what happens to this. The delta y and the delta x, those both become differentials. And so this turns into dy over dx. And what's that also known as? Where have you seen dy dx before?
The derivative of a function.
Yeah, it's just the derivative of the function. So what we're going to have here is f prime of x squared. All right, and that's the one you definitely want to box because, my friends, there is the formula. That is how we find arc length. So if you have a curve, you can actually determine its length by using this formula. Cool. Kind of cool. Always works. Always works. And it just comes from lengths of line segments. We're using line segments to approximate the curve. We just take an infinite number of them. All right, so really all you got to do if you got your functions, differentiate it, put that derivative into this, and then integrate this formula. Now, before we do it, though, I want to point out something else. Remember when I started here, I divided out a delta xi squared? I could have just as easily pulled out a delta yi squared, and things would have played out kind of the same, right? It just would have been a delta xi over a delta yi. And so since I could have done it that way, I can just as easily, let me write out another form for the arc length. I could have just as easily written it as arc length is equal to integral from a to b square root of 1 plus f prime of y squared dy. And this other form would be where we have our function as a function of y. So remember when we would turn our attention sideways, right? And we think about it as right minus left if we're finding the area between them or whatever. Well, this is for the turning it sideways, but you're not really turning the curve sideways or anything. You're just using the fact that it's a function now of y, and you still set it up the same way. So it's actually really, really nice how this plays out. All right, so we cool with the derivation, you cool with where it comes from. Well, let me show you an example. Now, one thing I am going to warn you about, the integrals that you get from these can be really gnarly. I mean, really gnarly. So it's just one of those things that we're going to have to pay attention to and realize. And so many of the integrals that we're actually going to get, even from nice curves, are going to require tricks that we don't know about yet. So when it comes to these, you're going to have to make use of technology. Use your TI-89, use Desmos, use whatever to calculate these integrals. And I full on totally understand that. So when I give you one, say on a quiz or an exam, if we haven't learned the technique to integrate it yet, I'm totally cool with using the technology. All right, I'm mostly going to look, did you get it set up right? All right, so here you go. Here's an example. And we'll start off really easy. We'll start off with the function that we tend to always start off with when we do this kind of thing. Let's look at x squared. And specifically, let's look at x squared from x equals 0 to x equals 2. Okay, so this is y equals x squared. And we're going to go from 0, 0 to 2, 4. So I want to figure out its arc length. Easy enough. No big deal. All right, well, let's get it set up. So in terms of its arc length, it's going to equal the integral from 0 to 2, because my x's are going from 0 to 2. The integral of the square root of 1 plus 2x squared dx. And that's all there is to it. So you notice our bounds, 0 to 2. We take the derivative of our function. So x squared's derivative is 2x. We fire that in. So this is the square root of or 0 to square root of 1 plus 4x squared dx. All right. There you go. Okay, he says, there you go, like it's no big deal. Getting it set up is absolutely no deal. Super easy. Now actually doing this integral, that's another story. It's a whole nother story. Because this one, we don't have the technique for yet. We're going to learn it later this quarter. I think it shows up in chapter 4. It's called Trig Substitution. And it's exactly what it sounds like. We're going to substitute in here with some trig functions. But we don't know how to do this one yet. So we'd have to turn to technology to get it for us. But let me show you what it would look like if we set it up with the dy, because this is an alternative choice, right? So I'm going to put a big or here, because we have another option. The other option would have been to set it up in terms of the y's. So if we were to do it this way, we're going to have an integral from 0 to 4, because those are now our y bounds, right? Y equals 0 up to y equals 4. We're going to have the square root of 1 plus. So the question of what goes in there, well, we need the derivative of the function as a function of y, which means I need to solve this for x. So if I were to solve this thing for x, I would get x equals the square root of y. So the derivative of that is going to be 1 over 2 square roots of y squared dy. All right, so these are going to give us the same values. This integral definitely looks uglier. It may not actually be, though. It may not be worse once you distribute and move things around and get it into a nice form. This one's still going to be ugly. But sometimes when you turn it the other way, you'll get a form that's a little bit easier to do. So either way, punch it in your calculator, you'll get your integral, you'll get your value. All right, so hopefully you're seeing the process. The only thing that's going to be a restriction on it is what was the derivative? How bad is that derivative? How bad was that original function? But in general, the integrals are going to be ugly because you have square roots of things with squares. Those are usually bad. All right, so any questions on the setup here? Are you going to be able to do it? Are you at least going to be able to get it set up on your own? Do you feel confident in that? Give me a thumbs up if you feel confident that you're going to be able to set these up on your own. All right, cool. I'm seeing all kinds of thumbs up. I love it. The integral, yeah, maybe. All right, but there you go. Another application of integral. Because we're doing the same thing that we did before, not finding areas, we're adding up. That's what integrals do. They add up little pieces. So we've now seen adding up areas of rectangles, adding up volumes of disks or shells. We've now seen adding up lengths of line segments. All right, so integrals, what do? They add up stuff, add up an infinite amount of infinitesimally small things. All right, so there you go. So arc length. Now, related to arc length is surface areas. Because suppose I did this, same line segment. But this time, what I'm going to do is I'm going to rotate it about an axis, kind of like what we did before. So let's just say we rotate this thing about the y-axis. So you can kind of see the shape that you're going to get. It's going to look like a bowl. But this time, instead of finding the volume of this, what if I wanted to know the surface area? So if I wanted to know the volume, you know what to do. You have a couple of choices. You can do it in slices and do the disk method. You can do it as cylindrical shells. Okay, but this time I don't care about the volume. I care about the surface area. What's the surface area of this thing? All right, now, if you need a reason for why you would care about surface area, the surface area would be like how much paint you need to cover it, as opposed to volume would be how much does it hold, right? Or how much material do you need to build it? That's your surface area. So surface area is actually an important thing in lots of scenarios. Maybe not any that you'll specifically do, but you can probably see why it might matter. All right, so that's the question. What is the surface area? Well, here's what we're going to do. We're going to do the same thing we've always done. Try to take over the world. That's your pinky in the brain reference. So we're going to do what we do every night. We're going to split this up into a bunch of little pieces. But now, this is what they're going to look like. So I'm going to have a line segment here, and the corresponding line segment on this side. And so I'm going to look at what's the surface area of that piece. And then I'll have another one with another line segment. Same story. What's the surface area of that? Let's put one more on here just for good measure. So another line segment. Okay, so I'm going to break it up into a bunch of little pieces again and add up their surface areas. Now, it might not be really clear what those little pieces look like, but this is what they look like. Let me draw one over here. They look like this. They look like the cone of shame that you have to put on your dog. We call it the cone of shame, right? But basically, it's the actual name for this. It's called the frustum of a cone. Don't worry about that if you don't know that name. Don't bother memorizing it or anything. But it's called the frustum of a cone, and it's basically just a piece of a cone. Right? Think about an ice cream cone, and we cut the top off. So we have a whole bunch of these frustums that we're going to be adding up. All right, well, if they're really, really, really thin, they basically act like a cylinder. They kind of look like a cylinder. So do you remember how to find the surface area of a cylinder? And it's okay if you don't know how to do that.
Pi r squared. No, that's volume. Would it be, is there a fraction in it?
There is not, but you are definitely thinking the right way, Suzanne. If we come back here, here's a cone, or a cylinder, sorry. So if we want to know the surface area, what we do is we actually take the circumference and we multiply by the height. Okay, so its surface area is its circumference times the height. And the circumference of that circle is 2 pi r. So the surface area of a cylinder is 2 pi r h. Now, this is going to be a little bit different because the h, right, is here as opposed to that little piece. But as this gets smaller and smaller and smaller, the h and the length here, we call that guy, say, L, they get to be about the same. Okay, so when it gets small, h is very much equal to L. So what we're going to do if we want to find this surface area is basically take all these 2 pi RLs and add them up. All right, well, what that leads to is this formula. The surface area is going to equal the integral from a to b, so from wherever to wherever, 2 pi r L and so there are going to be two forms. There's going to be the form for the x and for the y, depending upon which way we're, which axis we're rotating around. So the one form is going to be 2 pi f of x for our radius times 1 plus f prime of x squared dx. So just take a look at that for a second. So you notice that we've still got that, or I don't want f of x, I just want x. So we've got that square root of 1 plus, hold on, I did want that. I apologize. All right, so you see the square root of 1 plus f prime of x squared? That was arc length. That's our L, right? That's our height. The 2 pi is the 2 pi, but now that f of x is our r. So this would be if we were rotating it about the x-axis. So if we were to take a shape and rotate it around the x-axis, let me draw a picture so you can kind of see what everything is. So here's a curve. We rotate it about the x-axis. So notice that the radius, here's our radius right here, the radius of the circle, that's going to be determined by f of x. We're going to multiply it by a little differential line segment length, add them up, and that gives us our integral. Okay, so there's the surface area formula for rotating it about the x-axis. If we rotate it about the y-axis, like we did here, think about what changes. Now, here's my radius. My radius is going to be given by f of y. So it'll be 2 pi f of y, but the arc length formula still the same. It's just we're going to want it in terms of y. So the other option, if we go about the y-axis, it's going to be the integral from a to b, 2 pi f of y times the square root of 1 plus f prime of y squared. All right, so this is the one about the y-axis. All right, so let's see if we can set up the formulas for the surface areas. And let's start with the one that I just did right here that we started with. going from taking y equals x squared from 0, 0 to 2, 4, and rotating it about the y-axis. All right, so let's see if we can actually set that one up. I'm actually a huge fan of just remembering this. Remember that your surface area is the integral of 2 pi RL. Adjust it to whatever the specific scenario is. That way you don't have to remember multiple formulas. But if you like to have multiple formulas. All right, so let's see if we can set up the integral for this guy. So we are going about the y-axis, which means we are going to use this one. So its surface area is going to equal the integral from 0 to 4, because again, I need the y bounds. I'm going to have 2 pi times my function of y, which was the square root of y, times the square root of 1 plus 1 over 2 square root of y squared dy. Right, because if this was x equals the square root of y. So that's what this one's gonna look like. Again, we don't know how to integrate this guy, so we'd have to use our technology. So you're gonna notice that even with simple curves, like this is a really simple curve. Even with simple curves, these things can be pretty horrific in terms of their integral. All right, but I want to show you one that we actually can do, right? Because it sucks if we always get one that's like impossible, impossible, impossible. So let's set up another one, and we'll see that we can actually integrate it. All right, so this function, it's not that terrible of a function, but it's not as nice as x squared. Let's do this. Let's take e to the x. So we're going to rotate y equals e to the x with our x's between, say, 0 and 1. And we're going to rotate it about the x-axis. And I want to know what is the surface area of that shape. All right, so let me start with a picture over here. So e to the x, that looks like this. We're going to be between 0 and 1. Let's say that that's 1. So we're going to take this thing and we're going to rotate it around the x-axis. So we get this shape right here. Kind of looks like the end of a trumpet, right? End of a trumpet horn. All right, so I want to find its surface area. All right, so let's get this thing set up. We need an integral of 2 pi RL, right? That's in general what we need. So let's think about one of these circles. So what's giving us our R is the function value. So we're going to need 2 pi e to the x. Then we need our arc length. Well, since I've got x's here, and I'm going to be integrating it along x's for all those slices. We need 1 plus the derivative squared. Well, the derivative of e to the x, of course, is e to the x. And then we'll have our dx. So 2 pi times our radius times the arc length with our dx. And then the last thing, of course, we need our bounds, but we're going from 0 to 1. So there's our surface area. Let's integrate this one. So I'm going to rewrite this. It might help us see what's going on here. This is 1 plus e to the 2x, using the rules of exponents. So if I said integrate this with no technology, what are you going to try to do? What technique do you think might work here?
U substitution?
I think U substitution is a really good call. Maybe let's replace all of that stuff inside the square root with a U. Let's see what happens if we do that. If we let U equal 1 plus e to the 2x, what does du equal?
Just be e to 2x.
Not quite. Close though.
2e to the 2x?
Good. 2 e to the 2x. All right. So, and then a dx here, of course. So if we start replacing stuff, we have the square root of u. The dx is a du over 2 e to the 2x. Oh, I lied. I don't think we're going to be able to do this one. So one of the e to the x's cancels. So does a 2. So we have pi times the square root of u du over e to the x. So somehow we got to get rid of that e to the x. Well, we'd have to use this first equation and solve it for e to the x. So you get e to the 2x equals u minus 1. So e to the x is the square root of that. I actually don't think that that's any better. And the bounds on this are going to be from 2 to 1 plus e squared. Oh, yeah. All right. Never mind. We're going to punt. This form is no better. I thought when I set it up, the e to the x's were going to cancel, and clearly they don't. All right. Well, anyway, so hopefully you're at least seeing how we get them set up, but the actual doing of the integrals, they're going to be brutal. We're going to get forms that require things that we don't know how to do yet. All right. Well, there's some more geometry for you. Surface areas of surfaces of revolution and arc lengths are another place where we get integrals, and we get them because we're adding up lots of little pieces, just like when we found volumes and areas. All right, so a couple more applications for you. When we get back next week after taking the first exam here, we're going to keep going with some applications, and we're going to get away from geometry, because I know you guys are probably like, well, if all we're going to do is use this for geometry, what if I don't care about shapes? I'm going to show you some physics applications, and there are just so many, but We'll continue looking at applications, and then we'll start turning our attention to other techniques of integration. All right, but we have about a half hour left. And with this half hour, I want to talk a little bit about the exam, all right, like what to expect. So I'm actually going to hop back down so that I can sit at my computer and chat with you guys a little bit. But before I do that, any last questions on what was going on over here? Ignore this part. I'll do my Wizard of Oz thing. Ignore behind the curtain. But hopefully you're at least good with getting them set up. Because then it's just...
I have a kind of irrelevant question. So if we were like using technology, let's say like a drone to figure out the surface area, do you think like, I mean, I feel like people, because it's so long, because of the algebra, people will make a mistake. So would you trust, like in the future, if we were going to build something and have to use this formula in that way, would you trust to like do it by hand, or would you trust us to use technology if either way we were going to make a mistake somewhere?
Okay, so the thing about the technology is that where you're going to make a mistake there is the inputting of your information, because once it's in there, like that, our technologies that know how to do calculus, they know how to do calculus. They've been programmed properly. They do it right, with a few exceptions. So like if this was me and I was doing this for, you know, whatever sciencey reason, and I had to get an accurate number, I would go technology, and I would see what it gives me. But then I would also check to make sure that it was reasonable. But the number that I got kicked out from my black box seemed appropriate. You know, and what I mean by that is not, oh, the black box said it was 25.42 and it really should be 25.41. No, I'm not going to be able to discern the difference. But the black box spits out 25.42, and I go, no, it's got to be more like 2500, right? That's the kind of thing that you need to check when you use technology. That because you get a number that's unreasonable, that means you probably made a mistake in telling it what to do. So that's really the caveat with the technology is once it gives you an answer, think about that answer and go, does that make sense? Is it reasonable for the situation? Yeah, no, some of these things are so horrible that doing them by hand is going to require way more time and has just as much an opportunity for mistakes. So in an application setting, and I'm talking not in a math class, but you're using this because you're building a bridge or something, of course you're going to use the technology, but make sure it's a reasonable number, that it makes sense.
Thank you. That helps.
Okay, well, let me, I'm going to turn the screen off. Actually, I'll leave the screen on, but let me turn the other one on, and I will be right back with you. All right, so we have an exam on Friday, and I know a lot of you are probably a little bit nervous and unsure about it. So let's talk a little bit about it, what to expect, what kind of things are going to be on it, and so on. So first of all, the content, it's going to be chapter 1. So it's going to be all of chapter 1, and then the first 2 sections of chapter 2. So 2.1 and 2.2. So in terms of what's in there, chapter 1 is all about integrals. It's all about actually doing integrals and what they are and all that. And then chapter 2, those 2 sections, those are just areas between curves. That was 2.1. And volumes by slicing. So cross-sectional area volumes. So those are the only applications that are going to be on there. All right, so what kind of things do you need to know how to do? Well, if you go back to chapter 1, we started with the definition of the integral. And so you should be able to approximate areas using a certain number of rectangles. Like if I said, approximate the area under this curve using 8 rectangles of equal width using right endpoints. Right? So that was the old take your interval, break it up, use those widths, multiply by the heights. You get the heights by plugging numbers into the function. And that's where left endpoints, right endpoints, midpoints, whatever would give you those. But basically, that's just a geometry question. Multiply length times width and then add them up, right? So we approximated that way. And then you should also be able to use the definition for the integral, the limit definition. So that's the take a limit as n goes to infinity of the sum from 1 to n of your f of xi times delta xi. So what I'm talking about, if me saying that, you're like, I have no idea what you're talking about. Go back and look at quiz number 1, because quiz number 1, I had you do both of those things. I think for the approximate the area that was under a sine curve, it's either sine or cosine, something like that. And then I made you actually do calculate the integral of like a line, maybe an x squared, I don't know. But go back and look at those. You should definitely review your sum formulas. What you get when you add up i's, n times n plus 1 over 2. What you get when you add up I squareds, n times n plus 1 times 2n plus 1 over 6, and so on. You don't necessarily have to have them memorized because this exam is a take-home exam, right? You're going to access it the same way that you access the quizzes. So starting at 8:30, if you go to the link, you can pop it up and start working on it. You just have to make sure that you get it in on time, which I think is 11 o'clock. You can double check by looking at the syllabus. I think it also says on the assignment on Canvas what time it is, but I'm pretty sure it's 11 o'clock. But anyway, so since it's take home, you can still have access to all that stuff. So I would have that right next to me when I'm taking the quiz. That'd be one of the things I definitely have, those sum formulas for, you know, like I squared, I cubed, that kind of stuff. Anyway, so that's what we started with. You should be able to do it, right? You should be able to do the definition of the integral. If I ask you to use the limit definition to find an integral and all you do is the fundamental theorem of calculus, I will not give you any points. All right, I know that there have been shortcuts that we built later, but if I specifically ask you to do the limit definition, do the limit definition. All right, so then after that, we learned the fundamental theorem of calculus. I want to remind you that there are 2 parts to that. There's the part that we use when we're actually doing definite integrals, when we've got those bounds, right? And that's the one that says, well, take the antiderivative and then plug in the 2 endpoints and subtract, right? F of b minus f of a. So that form is super useful, and that form you probably don't even think about anymore because we've been doing it a lot. The other part of the fundamental theorem of calculus, that was the one that says if you differentiate an integral, you get what you started with. Don't forget that one because that's also really useful. We just haven't done much with it since we were introduced to it. So don't forget about that. So we talked about the fundamental theorem of calculus. We also talked about some integration techniques. So first and foremost, we did U substitution, right? So U sub, definitely know how to do U sub, and realize that sometimes you have to do multiple U subs. Sometimes you pick the wrong U sub. Sometimes you pick a U sub and there's still X's left over, but you can replace those using your original substitution, but solving for X. right? So there are some variations on that, but U substitution is a very powerful integration technique. So know how to do that. In addition to U sub, we looked at the integrals of exponents, exponentials, and logs, and inverse trig, and the forms associated with those. So the logs, anytime you have du over u, you get a log. For the inverse trig, remember there are the three different forms. And sometimes you have to do some algebra to get them into those forms. So one thing that we've done is completing of the square. I recommend practicing completing the square if you're not already very proficient with it. And the other thing that we did was long division. I saw long division was really useful. So practice your polynomial long division if you're not really proficient with it. So there are definitely some algebra tricks that we can use to help us out. With the trig, sometimes turning into sines and cosines helps. Like you may remember, that's how we actually got the integral of tangent, was we turned tangent into sine over cosine, and then we could do a u substitution with u equals cosine and blah, 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 blah. All right, so don't forget about your basic trig identities either. So you know how I mentioned I would have a sheet that has my sum formulas? I would also have a sheet that has the integrals of some of those basic forms of the basic function. So I'd have like integral of tangent equals integral of natural log equals, right? So I'd have that on my list. I would probably also maybe write myself a little bit of a note on things like with the inverse trig, you definitely should have the formulas for the inverse trig functions. But maybe next to that, say, complete the square, just as a reminder or something like that. Okay, so we talked about all those different techniques, and then there was the section that's called like the Net Change Theorem section or whatever. But basically, that was our first time of using the integrals for something other than areas. And that was seeing how the integral is basically adding stuff up. So those are the ones like you may remember on the last quiz with the tank, the leaky tank, the leaky oil tank. That one we integrated because we were basically adding up the leak as it went on, or the trying to find the displacement of a particle, because we had to integrate acceleration to get velocity and then integrate velocity again to get position. That's the one thing I do want to mention. Don't forget to do the second integral if you're going from acceleration to position. If you just integrate once, you get to velocity, which is great and answers lots of questions. But if you want to know position, you got to go one more step. Okay, so I think that's it from chapter 1 in terms of what was in there. So definitely know how to do those different integration techniques. So from chapter 2, things you should be able to do. Obviously, find the area between curves. Don't forget, sometimes it's easier if we look at them sideways. So if we make them functions of y. Also practice finding points of intersection, because that often tells us the bounds on our integration, right? Or that's how we find the bounds on our integration. So a big recommendation is to draw the picture. Draw the picture so you can actually see what it looks like. Because most of us, just given equations, it's not really clear what's on top, what's on the bottom, or what's on right, what's on left. So draw the picture. So know how to find those areas. I think that that's probably not that difficult now. Like looking back at it, you might have thought at the time, oh my gosh, this is hard. But now that we've been doing a lot of stuff with integration, you probably see that it's actually pretty simple comparatively. So then from 2.2, it is going to be volumes by slices. So the key thing to remember is you're finding the cross-sectional area. So thinking about slicing across it, what shapes do you see? Use those areas to help you set up the integral. So I do expect you know how to find the area of a square. I do expect you know how to find the area of a circle or a semicircle or some portion of a circle. I also expect that you can find the area of triangles. I know that when we did that one with the equilateral triangles, we ended up getting some crazy formula, right? You should be able to build that kind of thing from your knowledge of triangles. So I'm going to expect that. If it's some other weird area, like some other weird cross section, I will give you the formula. You know, like for example, let's say we took the cross section and it was hexagonal. I don't expect that you know the formula for the area of a hexagon. I don't. And I'm not going to make you build it during an exam. So I would give it to you. That probably won't be on there, anything like that. But just in case it is, I will give you that formula. Anyway, so know how to do that, and make sure you know if you're doing a solid of revolution, make sure to watch out for washers, because that's a mistake a lot of people make. They forget about subtracting out the little piece on the inside. So if it's not a solid region, if you don't get a solid, you're going to end up having washer method. So just watch out for that. That's not directed at anybody in particular. That's just being thrown out there with 20 plus years of teaching calculus. It's a mistake that happens all the time. Yeah. So when it comes to finding the volumes, if you end up deciding to use cylindrical shells, that's fine. Unless I specifically state, like if I say, you know, use volumes by slicing to find the volume, I don't really care how you do it. So if it's easier for you to do cylindrical shells, go for it. I think at this point, probably not, because that's still relatively new, but feel free to do that if you would like. All right, so I think that's pretty much all there is to it in terms of what the content is. In terms of what it's going to look like, just think about the quizzes. But like if you were to put the quizzes together that you've taken so far, that's a decent representation of what an exam would look like. I mean, obviously the questions are going to be different and all that, but you know, yeah, expect I'm going to give you a couple of integrals to say integrate this. There's going to be one that requires u sub. There's going to be one that, you know, there's probably something that gives you a log, probably something that does an inverse trig, right? Like the basic forms are going to be there. Expect a question, you know, use limit definition of the integral to find this. Expect some word problem-y type things, right? So that you have to actually integrate and then evaluate. So I think you kind of know what it's going to feel like. It's just going to be longer, right? It's a 2-hour exam as opposed to a 20-minute quiz. So figure, yeah, the equivalent of like 4 quizzes, plus or minus, is what the exam is going to look like. So at this point, you guys are far enough in your college and math careers that you know what to expect. There shouldn't be anything there that really catches you off guard. There probably will be some that make you think. I always do that. But nothing that we haven't talked about or you haven't practiced on homeworks. So anyway, that's all I really have to say about this. So I'm going to turn it to you guys. Do you guys have any questions? Are there any topics that you want a real quick refresher on? Because we still have about 10, 15 minutes left. And it's totally okay if there are no questions as well. Don't feel like you have to make up questions. Okay, so Alexi would like to see an example of a limit definition from the very beginning. I can definitely do that for you. Let me go to a whiteboard. All right. So let's just say we want to integrate, say, from 1 to 3. And we're going to do x plus 1 dx. But we're going to use the limit definition on this. All right, so it's going to be the limit as n goes to infinity of the sum from 1 to n. So always start with that. Every one of them should have a start that looks like this. But in general, what we're going to want in our sum is f of xi times delta xi. All right, so the delta xi, you're going to get your delta x always by taking b minus a and dividing it by n. Because we're going to take b minus a, that's that interval, and we're going to divide it into n pieces. So for this specific one, that's going to be 2 over n. Okay, so that's what we're going to put in there for delta xi. For what we're plugging into the function, you have some choices. You can do left endpoints, you can do right endpoints, you can do midpoints. It doesn't really matter. But I'm going to suggest that when you do this, what you plug in is a plus delta x times I. So this would mean you're actually using the right endpoints. And so for this one, we're going to do f of 1 plus 2i over n. So basically, since we're starting at I equals 1, we're going to do 1 plus a width. So that's going to be the right endpoint. And then we add another width, and another width, and another width, and another width, and it just kind of moves us down. Okay, so this is where you have to start. Get your delta x, use that to figure out what we're plugging into the function, and now let's plug it into our function. So we're going to get 1 plus 2i over n plus 1 times 2 over n. So that was my 1 plus 2i over n was my x. I'm adding 1 and I'm multiplying by my dx. Okay, so let's simplify this a little bit. 1 plus 1 is 2 times 2 over n is 4 over n. And then 2i over n times 2 over n is 4i over n squared. All right, so how are we doing so far? Kind of remembering this? Okay, so now let's do our sum. So I'm going to start with the 4 over n. That's constant in terms of I. In terms of my sum, that's a constant number. And so for constants, you get that times n. Okay, so now let's look at the 4i over n squared. We're going to get 4 over n squared. That's all constant in terms of the sum. But then we need the sum of I. And the formula for that was n times n plus 1 over 2. All right, so like I said, this is one of those things that I recommend that you have written on a piece of paper or something that's handy, so you can just jump straight to it. All right, so let's simplify this a little bit. So it's going to be the limit as n goes to infinity of 4, because the n's cancel. And then over here, I'm going to get plus 2 times n plus 1 over n. The 4 and the 2 reduce. One of the n's cancels. It's over here. We could even take this one step further. 2n over n, That's going to be a 2 plus the 4 is 6. And then I've got plus 2 over n. So now I take my limit. Well, as n goes to infinity, this goes away. And I'm left with 6. So this integral should be 6. Well, let's see. Let's check it. So I'm going to do the fundamental theorem of calculus on this, just as a check. So let's see, that's going to give us x squared over 2 plus x, evaluated at 1 and 3. So that's 9 halves plus 3 minus 1 half minus 1. Whoa, sorry about that. My pen is rebelling. Okay, let's try that again. Let me erase that stuff. Okay, so all right, so 9 halves minus 1 half is 4. 4 plus 3 is 7. 7 minus 1 is 6. Yay, we got the same number. All right, so that would be an example of finding the integral using the limit definition. Obviously, depending upon what the function is, right, you're gonna plug in different things. Depending on your bounds, the only thing that changes is what your delta x is. But you just go through the process and you'll eventually get there. All right, so is that kind of what we were looking for there? Does that help, Alexi?
Yes, thank you.
Yeah, you're welcome. All right, so I'm going to stop sharing there. So we still have a couple more minutes, so I got time for a quick question. All right, so it sounds like we're pretty good. Okay, so I'm going to go ahead and stop the recording then, and wish you guys a lot of success on this exam, and I'll see everybody on Monday.